Now we move on to VCF format. So the VCF format was originally proposed in 2011 to represent the variant codes from the large-scale genomic data set. And as we discussed in previous slides, this is a standardized format you can use for the genomic data set. So either you represent the variant alleles like SNPs, or in this, you put those variants into the VCF format. And also, if you call the structure variation, like a copy number variation, copy number deletions, duplication, whatever insertion, translocation, anything you can think about like a variant, we put on the VCF. And this VCF stands for the variant code format, right? And VCF has sort of this structure. So the structure has two parts. One is the VCF header, which is with this hashtag. We in computational science we call the comment, right? So if you use the hashtag either 1 or 2, that means that you leave some notes to people, right? So the computer cannot dealing with those information. It's rather discuss some information to other peers, the literally person, right? So within these comments, you have all the accessory information we call metadata, right? So metadata means that you have like a which version of file you stored in. So we say version 4.0, and which date you create those files, 2010, July 7th. And which bioinformatics tools you generate those information. You use the VCF tools, right? And which genomic reference you used, right? NCBI 36. And below that information, you have all the information we get from the VCF format. So if you go to the last line, which is just one comment here, you have several columns, right? So first column is the chromosome, second column is the position of where the variants locate, and variant ID. So it can be either like a SNP DB SNP ID, like an RS something. And you have the reference allele, which is the reference genome sequence. And you have an alternative allele, which we call variant. Now you know that, right? And you have the quality information. You have the filter information, which is based on this quality information, either passed or not passed, right? And you have the info column. Well, I'll explain you later, but briefly, info is the variant level information. So it's describing the variant information matching to each line. And the format is the sort of the same, meta information we see in the info column, but this is belong to genotype. So genotype is from each samples. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 columns. So all these 9 columns has the same format, whatever you see, any kinds of VCF, right? So if you see the VCF file I made, or if you create VCF file by yourself, you always get the 9 columns, right? And after these 9 columns, you have the columns afterwards. And those are the samples, right? If you put the 2 samples, you have 11 columns, right? Because you have 9 mandatory columns plus 2 columns for 2 samples, right? And each samples column, it contains the genotype information, right? So this is one example. If you look at this IGV plot, this is the one position having heterozygous variant, right? So if you look at those person, this person is the LF1396, which is paired in here, right? You have 9 column, and 10th column, you have the genotype information, which is 01. This represents for the heterozygous genotype. So this is the relationship between the variant and genotype. So variant is given for this locus, right? And here as well. So we have all the 4 genotypes, 4 variants, right? And if you look at the samples column, it has the genotype, right? So for this variant, this person, LF1396, does not have the variant. This person has the reference homozygous genotype, which is reference homozygous here, right? Briefly, we call RefHom. And normally, you not put this RefHom in the VCF file. But this is the, shorten the information. You have more columns. Let's imagine that. So one of the samples within this multi-sample VCF, you have the variant. That's why we put the variant information here. But if the VCF is just only for the single person, which is LF1396, you're not going to put this ref home information here, right? Because it doesn't point, right? This person doesn't have the variant. So why we keep this information, right? And if you look at the heterozygous, this is the 0-1, right? So which means that you have only one variant allele, right? It doesn't mean that either the first one, second one has those information, but conventionally we put the variant allele at the end, right? So if you go to the heterozygous, you put the 0 first and you put 1 later. This is most of the conventional situation, but I'll explain, additional situation afterwards. And if you look at the alternative homozygous, which is on both chromosomes in your DNA, you have the variant allele, then we put the 1-1. That's going to be alternative homozygous, we call the alt home, or variant homozygous, which is VA home, right? And if you go here, this is the unknown genotype. So you're not gonna get any genotyping on here. Why genotyping not happen? So this is one assumption. So if you look at this position, these two person has a heterozygous genotype, as we can see in a previous IGV plot, right? But if you look at here, you see that this person here has the reference homozygous because it doesn't have any variant allele within the sequence read, right? But if you look at here, this is an example actually from the deletion, but let's assume that we're not talking about the deletion here. We're talking about the missing the sequence read because something happens, so you're not gonna you didn't get any sequence reads here, right? So in this case, you cannot do the genotyping. Genotyping not possible. It does not mean that this person has certain variant or not. We don't know that information. So this is sort of the missing information. The case, you put the dot/dot, right? So this is the one when we describe the unknown genotype, right? Because of the missing sequence read, missing information, right? So back to the conventional notation 0-1, if you go here, there are some different ways. So if you look at here, so these say 1 pipe 0, right? 1 pipe 0, right? So this means that this is the phase data, which is you process the phasing. So now you know that the one of the chromosomes, you definitely know about where those allele locates, right? So if you look at the second variant and third variant, second variant appeared in the other chromosome, and the third variant is the first chromosomes, right? So you did a special process called phasing. Now you know that which chromosomes has which allele, right? But in most of the case, we're not using this phasing information because we don't need that, right? We just need the genotype information. So most of the situation you're developing for whatever the genetic analysis, we normally use the non-phase data. So you remember that we put the allele information like with the slash. So either it's B0 or 1, right? So this is most of the conventional situation for biallelic situation. Okay, so this is more examples of the variant format. So as we discussed previous slide, so the header sections represent the meta information, so same specs as we discussed before. And if you look at here, this is the again the same nine columns, and you have how many samples here? 1, 2, 3, right? And we put the sample ID here. This sample ID is mostly de-identified because genomic information is personal information. So we should put the de-identified samples rather than the actual names, right? So how many variants we can see? We have 4 variants, right? In the 4 locus, right? And the first variant, we have the A reference allele change to G, right? So this is A to G change variant. T to A, GTC to G. So this is the deletion, right? So 2 base pair deletion. And this is the SNPs, right? So this is an easy. What about this? This is, you can get either G or T. So A allele can change to G or T. So this case, we not call this is the multi-allelic. This is called multiallelic, right? Sorry, this is not a biallelic, so this is the multiallelic, right? So if you look at the info, it has the information like AN, AC, DP, AF, and you might find awkward. So you go to the header, then you get to know about what's that information. So AN is the allele number, right? So how many alleles you identified in these samples, right? We discussed in the section 3. So how many genotypes you have? 1, 2, 3, right? So all these three people has the genotyping information in this locus, right? So why AN is 6? Because 3 people and diploid genome, so 2 times 3, so it's 6, right? What about this? This person and this person has genotype, but this person doesn't have genotype, right? So it's going to be 4. That's simply easy. What about this? These 3 person has all the genotypes, so you're going to times 3. So AN is going to be 6. And here is as well. What about the allele count? Allele count is the number of alleles for variant allele, not the reference allele. So how many variant allele we have? 1, 2, 3. So it's going to be 3. And here's 1, right? And what about this? It has the either 2 or 3. Why? Because the variant allele can be G or variant can be T, right? So how many G is 2? How many T is 3, right? Because it's 2, 2, 2. Why is 1, 2, 1, 2, 0, 2? Because 0 means here, 0 always for the reference allele, and this is 1, and this is 2, right? So index is 0, 1, 2, right? It can be go to 3, 4, 5, 6. I even see like a 20, right? Because some of the genomic loci is so, polymorphic. So it has many, many different alleles across different people, right? So it can be happen. Oh, okay, so if you look at here, it's the 0, 1, 0, 1, 1, 1. So it's going to be AC is 4, right? What about the DP? DP is the depth, total depth. What that means, if you see here, you have an AD, which is a allelic depth, which means that if you look at this genotype, you can see that how many alleles you can expect. So this is an AD, so it's separated by colon, 29,1, which means that how many sequence allele for A here is the 29, right? How many G is 1. So how many depth you sequence on this locus, this person is 30. And out of the 30, 29 represent for the reference allele, right? So we can see that it's likely reference homozygous. What about this case? How many deaths? It's a 30 and 50%, 50%. So it's likely heterozygous. What about this? 050. So this person sequence 50, right? And it's close to 100. It's actually 100, not close to. So this is the variant allele, right? So this DP is the sum of the sequence allele across these 3 samples. So it's going to be 110. In 35, you sum up the numbers, you're going to have the 35, right? And this variant is the low quality. Why? Because if you look at here, the second information of the format, which is for the genotype, is the 3. So it's low quality, right? So it has the lower quality, the quality assumed as 3. And if you look at the low quality tag on here, it's describing the quality below than 10, right? So this is that information. And this is again the same, and allele frequency also the same information as we see in an AC. And biallelic sites is normally like an AA, AB, BB, Mendelian factors, right? So if you have this example, what is AA? Is a reference allele, AA. What about the heterozygous? It's AG. And what is the BB? What is the BB? Is the GG, right? And if you look at this information, the genotype information, genotype information format, you have the information like a GQ and PL. What is the GQ is the genotype quality, and what is the PL? Phred scale genotype likelihood scores, right? So PL is basically meaning the 3 different likelihood scores in Phred scales. So 0, 24, 900. And this Phred scales, PL, is basically representing the confidence scores, right? And the highest one does not mean that the the high confidence. In Fred's case, as we see last time, the bigger numbers comes in the lower things because it's minus log 10 value, right? So 0 is the highest confidence. So what is the highest confidence in this case? It's an AA, right? And second highest is AG, and third highest is the GG, 900. Why? Because this information is likely your reference allele. So a reference homozygous genotype. So reference homozygous genotype has the highest confidence and lowest Fred scale numbers, right? So that's why here. What about the GQ? GQ looks like a second highest one, right? Here. It's actually true because how we can calculate the GQ, we subtract the second highest PL to the highest PL, right? So 24 minus 0. So that's why it's going to be 24, right? Here it says what? The second highest is 60. So we had the 60, right? So do you think that the highest GQ is a good thing? More trustable? Yes, because you see the clear deviation between the highest confidence versus second confidence. So second confidence is lower and deviation getting bigger. That means that you have very, very high confidence for the highest confidence PL, right? So that's why GQ is working on that situation, right? So it looks like this is the highest GQ, right? This is not the 66. This is the 64. I typed wrongly. Anyhow, so this is basically ballpark of the VCF information. So let's look at 101. So if you look at the key terms in VCF, as I mentioned, the header contains all the meta information for variant calling process. So you put one comment for bioinformatics tool for mapping variant calling, and also you put the version of the reference genome, where you put the run date. And context is a chromosome, so the first one. And position of allele, you describe the variant location, is actually processed in one-based coordination. So this is the conventional notation for VCF. So what is the one-based coordination? You can think that if you look at here, so chromosome 1, the first position is T, and the second one is the A, and third one is C. And you have certain insertion variant happening here. You mentioned that according to the one-based thing, its position is on the it's on the fourth position, right? But if you think about the 0 position, it's between the 3 and 4, right? So you put the -1 position, right? So if you look at here, you say it's an AG variant happening around at the 14370 position. This is actually the position you're describing the one, but within the 0-based coordination, it's going to be 69, not the 70, because it's subtract 1. So this is how it works for the one-based pair, one-based coordination and 0-based coordination. In the VCF, we always follow the one-based coordination, but if you represent the information into the 0-based coordination in another genomic data format, that case you have to follow the 0-based one, and you have to subtract the -1 for position information. And the VCF has two types. One is the individual VCF, individual sample VCF, literally you genotype for only one samples, right? If you look at the multi-sample VCF, or we can say the joint sample VCF, this is more like an old term. This is literally genotyping for multiple samples, right? What is the good thing for multiple samples? It has the better quality for variant calling because you merge the multiple samples in your data set. You're basically generating the likelihood model based on the machine learning for quality distribution. So you see which quality is the good thing, which quality is the bad thing, because you know the background, right? So in this case, you can refine the high quality codes within your data set. So this is the beauty of the multi-sample VCF. And also, you can find the reference genotypes in all samples, right? Because as I mentioned last time in this slide, if you look at this column, if this is the individual samples, you're not going to get these lines because this sample doesn't have the variant on this position, and this one no, right? But if you have the multiple samples, you can see all possible genomic loci you can think of in the genomic analysis. So you can integrate those information. You can implement all different genomic analysis. You can fully utilize the reference genotype information. So this is also a good thing. What about the bad things in multisample VSEP? Because this is computationally slow and intensive. That's what I talked to last year lecture, but this year it was not, right? So last September, there was a new announcement from the Genomic Alliance, which is the international effort for the making trustful science in genomic field. And they announced that multisample VSEP is going to be standard in any kinds of genomic analysis afterwards, right? Behind that announcement, the issue was that the computational algorithm developed so rapidly. So nowadays, computational algorithm can solve those problems, right? So one example is in 6 years ago, when you're creating 10,000 papers multisample VSEP, if you use a super high computing system, it takes at least 6 months to make that VSEP, because it's like a 10 terabytes files in a compression form, right? But these days, algorithm develop so fast. You can use the deep learning. You can use all different, computational, engines like a cloud computing. So computation not really matter. So the algorithm can take those information. So if you want to create the 10,000 things, you're not going to take like a 6 months. You can only take 7 days. You can create the VSEP, right? So it won't be a problem, right? So that's why I say this is the old problems. So in your days, if you go to company, if you go to whatever the research institute, you're going to use the multisample VSEP. That's going to be the standard. If you look at the VSEP, we have the column called info, and this is the variant level information. Why? Because it can only describing the whether the variant happened at the locus or not, right? So we collectively call this is the variant level information. So if you look at here, so you have all these information, and these things doesn't have any meaning for the individual samples. It can only describing the variants happen in this locus, right? There and here, and this info is to describe the characteristics of variant you find in a variant calling. So it can have like this information. Also, we have the variant annotation describing where the variant comes from and how this looks like in population. So allele frequency and the genes transcript belong to these the variant and variant consequence as well. However, if you look at the VSEP format column, this is the genotype level information, right? So this is belong to individual levels, right? And the number of columns is same as the number of samples in the analysis, right? So describing the genotype information, as we discussed before, the GT information, AD information, DP, GQ, and PL, all these things can be possible in the format information. So PL, as we discussed in previous slides, this is the first scale likelihood of genotype, right? So if you look at the likelihood of possible genotypes, right, in your data set, so if you look at the biallelic sites, it can possibly 3 genotypes, right? AA, AB, BB. So you give the likelihood scores, like a confidence scores for the 3 genotypes, right? So AA is the homozygous reference, AB is heterozygous genotype, BB is homozygous alternative, right? And this PL is very essential because you're going to use for this genotype probability or calculating genotype quality information. So this is the case. So genotype quality, GQ, is the thing. You subtract the or the deviation between the second most likely genotype PR score to the most likely genotype, the PR scores. And you can calculate those deviation and you put the genotype quality information. And this is super useful because some of the variant codes are false. So you can easily remove those information based on the genotype, low genotype quality information. And if you look at the PL, let's back to the PL. When we describe the multi-allelic sites, sorry, this should be lowercase. And if you look at here, where we're going here is the AGT 3 alleles. So how many genotypes we can expect from these three alleles? This is like a factorization. So you're going to do the 3 times 2 times 1. Then there's possible things, right? So what is the genotypes you can think of is AA, AG, AT, TG, GT, TT, right? And all of that 6 information that's going to be stored in PL right here. So that's also possible in that information. Okay, so this is sort of the base backbone of the VCF. Then once you get the VCF information, you put those files into the variant annotation. So what is the variant annotation? So this is a process to assess the consequence of the variant from the variant calling. Why we need it? Variant calling does genotyping, that tells. So you have to know about what is the variant, right? So where is the variant located in coding or not, and whether the variant is altering protein coding sequence or not, and which genes this variant located in, right? So you can use the reference genotype data set for transcript or transcript sequences. Then you use that information, then you do the variant annotation. So some of the bioinformatics tools you can use for this information, one of the most common thing is the VEP, right? Ensemble VEP. This is the variant effect predictors, right? So if you go here, you can simply test by yourself. So on new jobs, then you choose one of the examples. I'll go VCF things. So since this is only needs the variant information, you don't need the genotype information because the variance is all same for everyone, right? And genotype is just either you have the 1 allele or 2 allele, whatever, right? The variant information is 165,568, right? If you know about that information, then you can set up those parameters and you can just press the go, right? If you take the run. We actually did the same thing when I recorded the video in Korean. So let's look at those information. So if you go here, this is one variant and second variant. And if you scroll down, you have the third variant comes from here, right? So what is this information? Why one variant? Why we have all that many things? Because it's annotated based on the transcript, right? So how many transcripts? So this is very like a gene and transcript centric information, right? So if you go the site, if you go the site in a genome browser, right? If you click that, let's zoom out 100. So this is the position. So the first position, this is the methionine, I guess. So if you look at here, this is the missense variant of these genes, OR4F5, right? It's the same gene? Yes, it is. So if you look at here, sorry. So this position is here. So this position is here, right? So it's, what is the position? It's the 6-8, right? So this is the 6-8. Why this is the 6-8? Let's look at it. Okay, so the position on here, right? So if you look at here, AAG is changed to CAG. Is that right? AAG, right? A is here. AAG is changed to CAG. So these lysine changed to Q, glutamine, right? And this is many things we can think of. This is the this is actually the zero-based coordination and one-based coordination is complex, right? So the variance is located in 6 to 8. So here's the 6 to 8, right? But the representation is zero-based, so 7 to 8, right? So -1. But VCF, since this is the one-based, so you have to think about like here, right? So anyway, so this is the one line of that information, this missense information, right? You know the missense, right? But why we describing this is the downstream gene variant? Because if you zoom out 100, downstream gene variant means that literally it's located in a downstream, right? So what is the downstream? It's probably here, right? It's the 8 to 6. Is that true? 8 to 6, right? So of these long non-coding RNA is a downstream of the variant. So variant located here, right downstream. And this gene OR4G11P, ORG11P. This is a downstream as well. So it's as I mentioned, that this is very gene and transcript centric. So we can describe that information in a multiple lines, right? Likewise, you can look at individual of them in a UCSC genome browser. You will find the same, the logic of that. Okay, so this is how the variant annotation is working. And since this information is done, you can store those information into the VSEF info, right? Because all that information is the same across all the genotypes. So it's the variant level information. This is the critical things. This is the variant level information. So you don't have to do these things is for the average genotypes, right? Only for one time at every locus, right? Every variant, right? You don't have to do that for the genotype, right? So what is the research for the variant annotation? You can use either protein sequence. So now you get to know about which protein coding, codons are changed, right? And you can expect that gene and transcript annotation. You can expect either transcription factor bindings or not. You can think about active transcription regions or not. All of this information, you can tweak the parameters up and down here. Then you can see that information too. And the format can be different by resources. So sometimes you use the GFF3 or GTF. Those things use the zero-based coordination, or you can use the BED files. This is all the zero-based formation. So if you go here, all of that information provided in a GFF or BED format. So you can utilize those information into the VP or the variant annotations. Okay, so this is basically the summary of how we can see the variant information in a certain type format called the VSEF, and how we can discuss that information into the genotype and variant level, right? So as I mentioned many times, this part is the critical thing. So you're going to view all the the genetic information, genetic studies and the papers we discussed afterwards, and also the exam papers is all based on this VSEF information. So please review this part thoroughly. If you have any questions, always come to me and ask the questions. And as I mentioned, and as I highlight again, this is the critical part for your final exams as well. So this is everything for today, and hope you see in a coming lecture. That's going to be 20, I guess. Yes. See you then.